Welcome to lecture number 11 for ECE 341, Random Processes. This lecture looks at a Pascal distribution. Now, a Pascal distribution is similar to a geometric distribution. It models the number of times you roll a die until you get R1s, or the number of times you make a trip in a car until R things fail, and it's time to buy a new car, or the number of days until R accidents happen at work and you're promoted, which is the Peter principle. So that's Pascal distribution, similar to a geometric distribution, which is roll a die until you get one success. This is roll a die until you get R successes. Now the PDF and mean and variance of the Pascal distribution are similar to a geometric distribution. The moment generating function is the same as the moment generating function for a geometric to the rth power. The mean scales by R, the variance scales by R. The PDF is a little bit different. Kind of what happens if I have to have, say, 3 successes. I have 2 successes in the previous R-1 trials, and the last trial has to be a success. So that's P to the R successes, Q to the X minus R, and if there's 3 successes, then the previous 2 successes could happen in any order, any spot, so that's X minus 1 choose R minus 1. So that's kind of the PDF for Pascal distribution. What has to happen is if I want to flip a coin until I have 3 successes, the last flip is a success. So this is going to be R minus 1, 2 successes on the previous K minus 1 flips. I've got that many successes, this many failures, and I have R minus 1 successes scattered around K minus 1 spots, plus the last time has to be a success, so it's going to be P times that. So this is the PDF for a Pascal distribution. It simplifies to K minus 1 choose R minus 1, P to the R, give the K minus R. Now the mean and variance of a Pascal distribution come from the moment generating function. The heart of a Pascal distribution is a geometric distribution with the Z transform of P over Z minus Q. If I have R geometric distributions, these multiply. So if they have all the same probability, it'll be P over Z minus Q to the rth power. To be a valid PDF, the 0th moment has to be 1. So plug in Z equals 1, and I get P over 1 minus Q, that's P over P, 1 to the rth power, that's 1. So this is a valid PDF, meaning the area is 1. All probabilities have to add 1. The first moment gives you the average, or center of mass. The first moment is minus the derivative at Z equals 1. So the derivative of P over Z minus Q to the rth power is minus R, P to the R, Z minus Q to the R plus 1 power, evaluate at Z equals 1. Doing some algebra gives you R over P. So not surprisingly, it's 1 over P times R. So this is the average, the center of mass. It's where Z transforms really shine. This is an infinite series, so trying to find the average for an infinite series is pretty hard. Not too bad with Z transforms. To get the variance, I need the second moment. The second moment would be the second derivative at Z equals 1. So here's the function, here's the first derivative, here's the second derivative. Plug in Z equals 1, and I get 1 minus Q, which is P, to the R plus 2. So R plus 1 over P to the R plus 2, P to the R gives you R plus 1 over P squared. Here's the second moment. Then the variance is the second moment minus the first moment squared. Plugging it in, I wind up with QR over P squared, which isn't surprising. For a single geometric distribution, it's Q over P squared. For R of them, it's R times Q over P squared. Surprise, surprise. Again, the variance measures the spread. So let's do a couple examples. Suppose I roll until 1 success. I'm going to roll a 6-sided die and a success is when I get a 1 or a 2. Now the probability of a success, P, is 1/3, Q is 2/3. So this is the PDF for a geometric distribution. In MATLAB, I have to go out to infinity, which is kind of a problem. So pick a number that's large, so large so I truncate it, I don't lose any area. So pick a number like 100 or 30. This has a mean of 3. If I go 10 times the mean, the area isn't 0, but it's pretty close. And if you're wondering, did I go far enough? This is the sum of A. It's almost 1. The part that I truncated is off as 5 times 10 to the minus 6. So not exact, but pretty close. That's kind of why I want 10 times the mean to capture most of the area. Once you get the PDF for a single exponential distribution, suppose I want to roll until I get 2 successes. So this would be a roll a 6-sided die until I get 2 numbers between 1 and 2. Or equivalently, number of times I do the dishes until 2 people notice, or number of times I go to parties until I get COVID, get 2 exposures to COVID, stuff like that. Those are all Pascal distributions. A couple ways to find that. One approach is to use convolution. Now this is an infinite series. As long as you go far enough out, say 10 times the mean, involve those together, I'll almost get the right answer. So take A, convolve it with A. And check. Is the answer 1? It's off a little bit. It's off by 1 times 10 to the minus 5. So again, I lost a little bit of area by truncating it, but not a huge amount. That's one way to get the PDF. Convolution. Basically, convolution is really easy with MATLAB. Just a pain in the tush by hand, but with MATLAB is pretty easy. A second way to get the PDF is use the formula. So I want to know the probability of having to roll the dice k times to get 2 successes, with the probability of success being 1/3. So that would be, here's P, Q, R. I'm going to go from 3 to 30. It's going to take at least, well, 3 means 2. 1 means 0 rolls, 2 means 1 roll, 3 means 2 rolls. It's going to take at least 2 rolls. That'll be n choose m, k minus 1, r minus 1, times p to the r, times q to the k minus r for k positive. And with a formula, I get the same answer that I got with convolution. Second way to do it. Third solution, I can use z-transforms. So this is the z-transform for a single geometric distribution. Here is 2 geometrics, Pascal distribution. From a table of z-transforms, here's the inverse z-transform of z over z minus a squared. So let's take this guy, multiply it by z, divide by z, pull out the 1/9. This has the z-transform of 2/3 to the k minus 1 times k, times 1 over z. 1 over z means delay by 1, so k goes to k minus 1, k minus 1 goes to k minus 2, u of k becomes u of k minus 1. That's the probability. If I check it, here's from the z-transform, formula, convolution, I get the same answers. However you want to do it, they all work. Here's another problem. Instead of doing the same die over and over again, suppose the odds change. So this could happen due to learning. Every time I run an experiment, I get better at it. Or I change the conditions, such as I'm going to roll an 8-sided die until I get a 1. B is roll an 8-sided die until I get a 1 or a 2. C is roll an 8-sided die until I get a 1, 2, or 3. What's the total number of die rolls? Well, that's the Pascal distribution. This is where z-transforms really shine. This is the PDF of A, exponential, PDF of B, PDF of C. In MATLAB, I can grind out what those are equal to. Just have k goes from 0 to 100. And here's the values of a, b, and c. Once I get a, b, and c, I can convolve them. Convolve a and b, I get a, b and c, a, b, c. This is the PDF of the total number of die rolls. That's the Pascal distribution. And that's going to take at least 3 rolls to get 3 ones. The highest probability is right around here, about 9 rolls. The average will be something else. A second way to get that answer is z-transforms. Here's the z-transform of A, z-transform of B, z-transform of C. Add them all up. In the z-domain, I multiply. So this is the z-transform for the sum of A, B, and C. Now take the inverse z-transform. So what I'm going to do is do a partial fraction expansion, multiply both sides by z, take the inverse z-transform, now divide by z corresponds to delaying by 1. So this is the PDF for a plus b plus c. If I check the answers, here's using convolution, here's using the z-transform, the answers match. Again, either way is valid, give you the same results. Kind of notice I get no results up until 3, so what I could do, well, that shows up right here. I've got a 1 in the numerator, z cubed in the denominator. That means delay by 3. What I could do is multiply by z cubed on both sides. Do partial fraction expansion, pull out a z, z squared. I'm going to get different answers. Then divide by z cubed would be k minus 3, which means nothing happens until k equals 3, which is kind of what you see anyway. I'll get a different way of expressing the answer, but the answers are equivalent. So there's a couple of ways to do this. Third example. Suppose I want to roll an 8-sided die until I get 4 ones, roll a 6-sided die until I get 2 ones. What's the PDF for the total number of rolls? Well, this is where convolution is pretty easy. Here's the PDF for an 8-sided die. The average is 8. I'm going to go about 10 times out, 100. PDF for the 6-sided die. Make sure that the first entry is 0. 0 means 1 means 0. It takes at least 1 roll to get there. Okay, 2 8-sided dice can involve d8 with d8. Gives you 2 8-sided dice. Can involve those. I get 4 8-sided dice. Well, 2 successes on the 8-sided die, 4 successes on the 8-sided die, 2 successes on the 6-sided die. Combine them. 4 successes on the 8-sided die, 2 successes on the 6-sided die. That's the PDF. And checking to see I went far enough out, the total probability should add to 1. It does, at least 4 decimal places. If I do a bar chart, that's the PDF. So here the maximum likelihood is right around here, right around 36 rolls. That's not the average, that's the maximum likelihood. That's one way to do it. Come up with an equation for that function. Well, this is where z-transforms are kind of nice. The z-transform for a 6-sided die is 1/6 z minus 5/6. Z-transform for the 8-sided die is this. So 2 6-sided dice, 4 8-sided dice, that's the z-transform for x. Now take the inverse z-transform. This is not going to be fun. So if you have a hard problem to solve, there's a couple ways to solve it. An engineering solution is, if I have a hard problem, change the problem. But change it in a way that I keep the flavor of the old problem, but make it easier to solve. The problem I have here are repeated roots. So rather than have repeated roots, I'm going to change them. And take this root, make one root slightly smaller, one root slightly larger. And take these 4 roots, make one smaller by 0.002, 0.001, plus 0.002, plus 0.001, something like that. This is almost the same problem. Not exact, but if I change the probabilities to the third decimal point, I'm going to be really hard-pressed telling the difference. That's typically what you do in engineering. Change the problem to make it easier to solve. With this change, I no longer have repeated roots. I no longer have to worry about that special case of what do you do with repeated roots. I can use my partial fraction expansion just like before. The numerator has to be whatever it takes to make this a valid PDF. The 0th moment has to be 1. So doing that, here's the numerator makes the 0th moment 1. This has a delay of 6, z to the 6th in the denominator, nothing in the numerator, so denominator 6 orders higher. Let's multiply both sides by z to the 6th. When I do that, I can do a partial fraction expansion, pull out a z, partial fraction, put it back. This will be something in this form. Once I find a, b, c, d, e, f, take the inverse z transform, that's easy. Then divide by z to the 6th. When I do that, all the k's go to k minus 6. So there the result will be almost the same. So here's my poles. I'm going to do a partial fraction expansion. So for the first pole, at z is 0.8323 plus epsilon. Again, I can't make this exactly the same because then I get 0 over 0. MATLAB doesn't like that. Perturb it just a hair. Find a by multiplying g of z times z minus 0.8323. Evaluate at z is 0.8323 plus epsilon. Evaluate, that gives you a. Then b, then c, d, e, f. When I'm all done, this is y of k. And here's the equation for y of k. If I plot the two together, this is answer using convolution, answer using z transform and an equation. The blue line is convolution, the red line is the equation. Basically the same. Not exactly the same because I changed the problem, but close enough it's really hard to tell the difference. That's an engineering solution. So that's a Pascal distribution. A Pascal distribution is an extension of the geometric distribution. It's the number of rolls until k events happen. This is where the z transform really shines. They make computing the mean and variance a whole lot easier. They make combining geometric distributions a whole lot easier. I can also use convolution. Convolution pretty much always works. But if I want a closed form solution for what the PDF is, I kind of need to use z transforms. And the last thing to note is if you have a problem that's hard to solve, what I can do is change the problem. Change it in a way that makes the problem easier to solve, but also change it in a way that you keep the flavor of the old problem. For example, back here, I have 2 roots at 0.833, 4 roots at 0.8750. If I instead put the 4 roots slightly different, I change the problem, but not a whole lot. Take these 2 roots, change them just by hair. It changed the problem, but not a whole lot. So the answer I get for the change problem will almost be the same as the actual problem. That's lecture number 11 for ECE 341, Random Processes.